Hi, I'm Eva Murphy from Electronic Engineering at IT Sligo, and this is my Leaving Cert Maths Grinds channel. I'll regularly add new videos for both higher and ordinary level maths, so make sure you subscribe below and click the bell icon to be notified of new videos. Okay, the 2016 question, I think this was question 7 on paper 1, calculus, more rates of change, real rates of change section in towards the end of the calculus, the differentiation chapters. Air is pumped into a spherical exercise ball at a rate of 250 centimeters cubed per second. Find the rate at which the radius is increasing when the radius of the ball is 20 centimeters. Give your answer in terms of pi. Okay, a lot of students really struggle with rates of change questions. So let's tackle this one. Find the rate at which the radius is increasing. Okay, so that's kind of the first thing I look at, which is this. Okay, so when you see a rate or a rate of change like that, it is with respect to time. Okay, so what does that mean? Well, if you're going to find the rate of change at which the radius is increasing, then radius is r, and it's with respect to time. Okay, so that's the first thing to figure out. What exactly is this question asking from me, and try and write it in calculus notation. So this is the rate of change of radius with respect to time. Okay, and air is pumped into an exercise ball. Okay, so if you think about a ball and you're pumping in air, the ball is getting bigger. But what of the ball is getting bigger? Yes, the size of it, but in mathematical terms, what is it? Well, it would be the volume of the ball, okay? So if we go back to our area, right back to our area and volume pages at the start, we have a sphere, which is your ball, and your volume is 4/3 pi r cubed. Okay, so volume of the sphere equals 4/3 pi r cubed. Okay, so that's the volume. I'm just going to write it as a letter V for volume. Okay, so if I could differentiate this, if I could look at the rate of change of this, volume could change, but only with respect to radius. So 4/3 is a constant, pi is a constant. So the only thing I can differentiate this formula with respect to is the radius. Okay, so if I differentiate that with respect to the radius, it's the power of the radius that comes down and reduces by 1. So 4/3 by 3, the 3's will cancel, so I will have 4 pi r squared. So that's dv dr. Okay, and I need dr dt. Okay, so this is what I want. Okay, so I know I have a dv dr. Okay, so what have I done here? In many questions for rates of change, you get at what you need by breaking it into 2 parts, okay? I will differentiate something with respect to the radius and something with respect to time, okay? Now I see in here I have a dr, okay? If I flip him, then I will have dr over dv, okay? And I get 1/4 pi r squared. Why am I doing that? Well, I'm doing that because I can see that I could put dr dv in here. Okay, so therefore dv has to go in here. Now, what am I doing? Let me just explain that a small bit. I want the rate of change of radius, okay, with respect to time. I have a formula here from the volume because the volume is changing. The only thing I can differentiate that with is respect to the radius. Okay. How did I build up this one? Well, I know I need dr dt on the top. So I'm going to have a dr here. I know I need a dt on the bottom. Okay, I know there's nothing up here that's going to give me the rate of change of radius with respect to time directly. So it's an indirect calculus. Okay, so when I saw dr appearing here, I reckon if I flip that, then I could put my dr dv in here. Okay, now why did I put dv up here? Well, because in effect, I can cancel them two, if you can see that, and I'm left with dr dt. Okay, so that's where I'm going. And that's, I suppose, why I've broken it up the way I have. And then we try putting values in here. So if I can come over here, my dr dt is then equal to dr dv 1 over 4 pi r squared. Okay, the rate of change of volume with respect to time, well, isn't this a rate of change of volume with respect to time? Okay, so in fact, I have a value for that. Okay. So I hope that makes sense. You can, of course, write it as 250 over 4 pi r squared. Now, the rate of change, the rate at which the radius is increasing when r is 20 means I sub in 20 in here. And if I put that into the calculator, by 20 squared. Give your answer in terms of pi. Okay, I'm getting a decimal when I put it into my calculator. So let's go 250 on the top, and on the bottom I'm going 4 by 20 squared. I'm getting 5 over 32. Okay, and I'll just leave the pi at the bottom. So what did I do there? Well, when I put all that into the calculator, I got a decimal. It asks for the answer in terms of pi. I actually looked up to see how many decimal places, but it's not in terms of pi. So I left that out of my calculation. I put the rest in, and then I just put the pi back in on the bottom. So 5 over 32 pi is what I get my answer for that. So the rate, my radius was in centimeters. So it's centimeters, and it's time, it's rate, so it's per second. Second is the scientific unit of time. Okay, so the rate of change questions, once you get your head around this part and work from whatever formula they're giving, they're doable, but they're quite a hard section, I think, a hard enough question of calculus. Find the rate at which the surface area of the ball is increasing. So it's still a sphere, still a ball. Okay, surface area is here. I know that because A represents the curved surface area and V is the volume. So A is equal to 4 pi r squared. Find the rate, so rates of change. Okay, so that's how you know that you need to differentiate it. Find the rate at which the surface area of the ball is increasing. So again, I can only differentiate that with respect to the radius because 4 and pi are constants. So 2 4s are 8 pi r. Okay, find the rate at which the surface area of the ball is increasing. At the rate that the surface ball is increasing. So it's actually dA dt that I need with respect to time. Okay, so I won't get it directly. So dA, that's bad writing, dA on the top, dt on the bottom. Have a look up here and see what we have to work with. We have a dr and we have a dr. Okay, so he's fine, he's good, he's going to slot in there. Now d or dt, do we have a rate of change of radius? Okay, have we a rate of change of radius anywhere? Well, yes, we have. That should ring a bell from here, okay, because the ball is still 20 centimeters. So therefore, for this one, I'm going to get 8 pi r, and it's multiplied by 5 over 32 pi. I'm taking that from here. Okay, let's put him into the calculator. Our pi's are going to cancel. So, oh, I have to sub in the 20 for the r as well. Let me do that. 8 times 20 by 5 over 32. Let me put that into a calculator. 8 by 20 by 5 on the top over 32. And I'm getting 25 for that. Find the rate at which the surface area per second. Okay. So that is the rate that the surface area of the ball is increasing. Okay, the inflated ball is then kicked into the air from a point 0 on the ground. Taking 0 as the origin, x, comma, f dash x approximately describes the path followed by the ball in the air, where f of x is equal to minus x squared plus 10x. Find the values of x when the ball is on the ground. So the inflated ball is kicked into the air from the ground, okay? So I hope you're okay that it's going to start and a ball goes up, a ball comes down, okay? Or that's the trajectory I would expect a ball to fit. So I would expect one of the times that its values, one of the times it's on the ground is at 0 and then after a length of time. Okay, so how would I do this one? Well, find the values of x when it's on the ground. So at the x-axis, my y is 0. Okay, so f of x, which is equal to y, is equal to minus x squared plus 10x. Okay, so put in your 0 for your y. You have a couple of options for solving this. You can write it as a quadratic if you want. You could do the minus b formula if you wanted, where a is minus 1, b is 10, and c is 0. That's perfectly okay. Or you can factorize it where you take out the x, and I'm left with the minus x plus 10 equals 0, or 0 equals, whichever way you want. Okay, and then you let each factor equal 0. And then you let this one equal 0. So just like you would in a quadratic. So x is equal to 0 and minus x plus 10 is equal to 0. Bring over that, x is equal to 10. So find the values of x. Okay, and that makes sense from if you think about the physics of a ball being kicked up and back down again. Okay, and then part 2, find the average height of the ball above the ground during the interval from when it is kicked until it hits the ground again. So these words, average height, that's a clue for the average area under a curve formula, which is part of integration. Interval is another hint that it was integration that you were doing. So basically, a way of getting the area under the curve is that chapter on integration. Okay, average area, there's a formula for it. It's 1 over b minus a, the integral between a and b of f of x dx. Okay, so that's a formula, and that's a formula that's not in the log tables. You have to learn it. Your b and your a are the points that you're integrating between. So you're getting the area under that curve between these 2 points, which we call a and b. And f of x is the function that describes the curve that you're getting the area underneath it. And then this piece, this whole thing just averages it out. Okay, so that you get a rough area under that curve. Okay, so for this one, it would be the integral between 0 and 10 of our function. I forgot the 1 minus b minus a part before it. Back up there. 1 over b minus a, the integral of my f of x, which is minus x squared plus 10x dx. Okay, so I'm getting a 10th, and then to integrate that, you add on a power and you divide by your new power. You add on a power and you divide by your new power. Okay, and it's between 0 and 10, these two values here. Okay, now I didn't leave myself enough room for that. Let me come up here. Okay, so I'll just come up here so I'm not squishing. So it's top minus the bottom then, so 1 over 10 times the top number. So I sub in 10 for x, that's what I mean by top. Okay, so I'll have minus 10 cubed over 3 plus 10 times 10 squared over 2. And of course I could simplify, I just haven't bothered, minus the bottom. Okay, so there's not much point in subbing in the 0. That's going to be 0 plus 0 here, so I can just minus 0. Okay, and of course it's a 10th of all of this. Okay, so you can put that into the calculator, and I get minus 10 over 3 plus 10 squared is 100, by 10 is 1000 over 2, so that's 500. Of course, it's a 10th of that. Now I can't do any more in my head. 1 over 10 bracket minus 1000 over 3 plus the 500. And I am getting 50 over 3 for that, or 16.67. And it's the average height, so it's meters. Okay, so the average height, you should know it's that formula. You'll always see this keyword average and then interval hints that it's integration, so the area under a curve.
If you've enjoyed this video, then why not join us in IT Sligo and use maths in practice. In conjunction with industry, we've designed an exciting new program in electronics and self-driving technologies, which uses cutting-edge techniques such as artificial intelligence, computer vision, and virtual and augmented reality. You'll need a H5 in maths to qualify. Check out the link below.